Hello and welcome to this session on mechanical design. I'm going to review today for you a very short review highlighting some of the main aspects of the course which would be important as you prepare for the final exam. So let's start first talking about failure theory, and here I'm going to give you a quick view of failure theory and how it is used in actual example. So as we know, failure theories, we've described it starting from maximum principal stresses, which is basically a box in 2D, and this box has limits, and the limits are dictated by the yield strength of the material. So we have to find the two principal stresses, sigma 1 and sigma 2, and that we must know Mohr circle on how to convert a biaxial stress state that has sigma x, sigma y, and tau xy to a equivalent principal stresses, sigma 1 and sigma 2. And then the second theorem that we discussed is the maximum shear theory. And in this theory, we have to find the maximum shear, and the maximum shear is typically the difference between the largest and the smallest principal stress divided by 2, because this is the radius of the Mohr circle. And in this case, we get the Tresca hexagon, in which we have to identify the quadrant that we are working with. If it is quadrant 1, it has positive sigma 1, positive sigma 2. If it is quadrant 2, then it will have negative sigma 1 and positive sigma 2, and so on. So in this case, we have to be cognizant on which quadrant the stress state is going to be, and then we apply the appropriate limit as we've learned in class. The next theorem is the distortion energy criterion, and in this case, we find at the end of the day the equivalent stress, and the equivalent stress is the von Mises stress, from equating the distortion energy in under triaxial conditions to the distortion energy under uniaxial conditions at failure, dictated by the yield strength. And therefore, we find that we have a definition of the von Mises stress, and that for plane stress, we have sigma x squared plus sigma y squared minus sigma x sigma y plus 3 tau xy squared, all to the 1/2, so the square root of all of this quantity. Under 3 triaxial conditions, we have a longer expression, but we rarely use it in class because we usually have shaft design is mainly either due to torsion and bending, and even if we have an axial force, we usually end up with a biaxial stress state. So we usually use this form, and we use it to equate it to the yield stress at failure. So it gives us an ellipse, as we have discussed it, and therefore the ellipse is encircling the Tresca hexagon, which means that the von Mises is less conservative as compared to the Tresca. So Tresca condition, or the maximum shear, is more conservative. And then we moved on to Mohr theory, and in Mohr theory, we just accounted for the difference between tension and compression and extended the Tresca hexagon to become, in as you can see here, in 4 quadrants, where the tension has a small box. Usually the tension, the stress that is required to yield the material under tension condition is S sub T, which is smaller than S sub C. S sub C is the stress that is required to yield the material under compression. So we have to be cognizant again of which quadrant we have the stress state, and then use the appropriate equation, either a simple limit like S sub T or a straight line description of the limit that we have to use to solve for the factor of safety. So these are this is a quick review, and we could also, for some brittle materials, extend the condition, the more yield condition, to be a little bit less conservative, and that is by extending the maximum principal stress when under compression to be on the negative side before we apply the linear relationship that we had in quarter 4 or the second quarter, as you can see here. So it is going to be somewhat less conservative than the straight Coulomb Moore that we have studied. So that's kind of a summary. So let's now take an example to discuss how that can be applied. In this example, we have a bar, and the bar has a round cross-section. It has a diameter of 2 inches, and it has a shoulder that has stress concentration because the diameter is reduced to 1 inch. And then we have another bar that has a length of 15 inch, and we have force F applied at the end. So this kind of problem is intended to give a relationship between the applied forces and the stress state that can cause failure. And therefore, we would conclude that the stress that can cause failure is at point A, as we discussed it before. So you have to look for that. And not only that, but you have, if you have this round bar on the top side, the stress state is going to be, it has bending because the force F is bending it downward. But if you look on the side here, then you find that it has torsion, and therefore you have more shear on the sides. In other words, we have to be cognizant of relating the applied forces to the resulting stress state, whether it is at point A or point B or point C, whatever point we choose, you have to be able to find an element and then find the corresponding stress state on that element. So in this example here, we have sigma x. Sigma x, it means it's axial, and the axial is because of bending, and therefore it is M over IC with a stress concentration factor that would be obtained from the book, in which we have charts to get the stress concentration factors. And therefore, we will be able to find the axial stress if we know the force F. We can also find the shear stress, and the shear stress is because of the torsion part. So we have to know that if we have a force here, F downward, is going to cause bending on that section of the bar, and it's going to also cause torsion because F times 15 is the torque that is applied. So in this case, we can find the shear stress that is acting at the same point A. Once we find the stress state, as I said, axial and shear, that's mostly what we have in shaft design that we discovered by now. We have to convert that to principal stresses, and then once we convert to principal stresses, we can find the maximum shear. So it's very important to enact that conversion. So you have shear due to torsion. That's not the maximum shear, by the way. I think we talked about this in the midterm. So shear due to torsion, and you have an axial stress. You combine them in such a way that you get the maximum principal stresses sigma A and sigma B. So that, as we've seen, the maximum stresses is sigma x plus sigma y. Here sigma y is 0, so it'll be plus 0/2, plus or minus square root of sigma x minus sigma y over 2 squared, plus 3 tau squared. So we have this formula that we use, and it gives us the maximum principal stresses. And then we are home free. Once we get the maximum principal stresses, we could use any of the 4 different criteria or 5 different criteria that we discussed for failure. So you can imagine that you can use it for brittle Coulomb-Moore to determine the maximum value of the force F for a given stress concentration factor, or if it is modified more, then you have to test whether sigma B over A is greater than or less than 1, and therefore in the fourth quadrant or the second quadrant, that will tell us whether we use kind of a straight limit or we're going to have to use a straight line equation to determine the maximum value or the value of the force that causes failure. So to summarize, as we said, we have a brittle failure is when the ductility of the material is limited, like 5% or less. And in this case, we have to consider either conservative design or a less conservative design. If it is conservative, then we use the brittle Coulomb-Moore. If it is less conservative, then we can modify the brittle Coulomb-Moore by extending the fourth quadrant or the second quadrant to give us a little bit more of a design space. And on the other hand, if the ductility of the material is greater than 5%, then we know that we have ductile material, and we're faced with another decision. If the yield stress in tension is equal to the yield stress in compression, then we go down that route and we consider conservative design due to, then we would use, if it is conservative, we use the maximum shear stress theory, MSS. If it is not conservative, then we would use the distortion energy, which is the ellipses inside the Tresca prism. So if the yield stress in tension is not equal to the yield stress in compression, that would be good for the material, because you can imagine that in this case, the yield stress in compression is going to give us a larger design space if the material is under compression, and we use the ductile Coulomb-Moore under these conditions. So once we have this idea, then we would be able to discuss the failure criteria in under any circumstances that we have here. So now I'm going to switch gears, or kind of change the topic a little bit, and I'll stop the sharing of the screen here and get another example. And this other example is going to be related to another design problem that relates to the conditions for Castigliano's theorem, as we've learned in class. So we have here, we're going to start and do a share. And if we discuss Castigliano's theorem, its importance is that we can immediately determine deflection at any given point without having to deal with integrations of the equations that go from the load to the shear force diagram to the bending moment diagram to the deflection. So we didn't have to do all of that, and we have a direct way to compute the deflections. So to summarize, we have now the deflections. Let's see if we can get it right here. I have to do a new share for this condition here. And I'm going to share with you the equations for Castigliano's theorem. As you will see here, that we have the deflection is the rate of change of the elastic energy with respect to a force that at a given point. And the deflection is always in the direction of the force. So if it is axial, the tension compression, we have this expression, 1 over AE times F dF by dFi, where Fi is the specific force. So we have to find an expression for the force in general, and that expression has the force that we are interested in, and then we take that derivative with respect to that force. So it's a little bit, you have to be careful how to write the expression for the force in terms of the specific value that you're interested in. If it is torsion, then it would be 1 over Gj, T times dt by dmi. So this is the torsional rate of change of the angle. And for bending, if we have bending situation, the delta I would be du by dfi. And we found that it's 1 over EI times the product of two terms. One is the moment, and the other one is the rate of change of the moment with respect to the force Fi. So let's try to see how we would apply this to a given problem that we discussed before. If we have a curved beam, for example, the curved beam has a force system. If we have a force that is applied, let's say, in the horizontal direction F here, and then you take a cut anywhere in the beam, then you will see that you will have a moment at that section, and you will have an axial force F theta and the radial force Fr. So it's kind of a complicated force system, and each one of these components stores elastic energy in the curved beam. And what we discussed is that we need to be cognizant that the elastic energy due to the moment is m squared d theta over 2 times A, the area, cross-sectional area of the beam. E is the difference between the radius to the centroid of the beam minus the radius to the neutral axis. So this is eccentricity that we need to determine. So if we apply this equation, we need to figure out what is the neutral axis radius and what is the radius to the centroid of the beam. And then when we take derivatives, we will be able to utilize this equation. And then we have a component of the energy due to the axial force F theta, because it's same. F is F squared dx. dx becomes RD theta over 2AE. And then we have another component due to, once we have the axial force, then we have other components that come in. One is due to the counteracting moment of F theta, because F theta wants to pull back the beam. So it's kind of a negative subtraction. We have to subtract this amount from the bending energy, mF theta d theta over AE. And finally, we have another component due to the shear force, and the shear force is caused by Fr, the radial force with a factor, a shape factor, because the shear stress is not uniformly distributed over the cross section. So these are 4 different terms, and therefore, if you're solving a problem with a curved beam, then you have to do a lot of work, because you have a moment part, you have another axial part, you have an interaction part between moment and axial, and then you have a shear part. So in our problems, we considered, we could, of course, if we have time, we could do all of this, but for the exam or for most practical problems, If the curved beam is very thin, it has a large aspect ratio, the ratio of the radius of curvature to any of the dimensions of the beam, the cross section of the beam, the diameter, for example. If that ratio is greater than 10, then we can safely disregard the contributions due to the radial force, which is the shear component, due to the axial force, which is the tangential component, and due to the interaction force or the reduction in the bending energy due to the axial force F theta. So in this case, we have only the first term that we would consider. And here you have to kind of review these equations to be familiar with those. And therefore, we get to a point where we could use just like the first term here. You can see this is the first term that we can use. The other terms are typically small in value compared to the first term. So let's continue on. In case also that R over H is greater than 10, there is a very useful approximation that the deflection becomes simpler. We have m squared r d theta over 2ei. So this is almost the same as a straight beam, a beam that is straight. In other words, instead of dx, we would have r d theta. That's the same equation we use for a straight beam, but we just should substitute r d theta in place of dx and do our work. So let's take a quick example here, which is an example that we discussed before. If we have a straight section and a curved section, and we have a force applied to that curved section at P, then we have to consider the contributions to the deflection. In this case, in this example, they want us to find the deflection of the tip D downward. So if you look at the tip D, it will deflect downward and sideways. So it has like it's like two-dimensional, it's like a vector, but they wanted us to determine only the deflection downward. And therefore, we said if we don't have a force, then we pretend that we have a force on D. We call it Q, and do the work as if there's a force. And then before we evaluate the deflection, we just substitute Q equals 0 in the final equation because it's a dummy force, and we get the result. So here, if we take that, we have to, if we want to find the deflection at D, we have to consider the energy stored in AB, the energy stored in BC, and the energy stored in CD. So in this case, by common sense, there is no energy stored in CD because it doesn't have any force applied in reality. Therefore, we consider only AB and BC and find their contributions to the deflection. The other point that we mentioned several times is that we have to be thoughtful about the selection of the coordinate systems. So for AB, we can start it from point B and then take the x-axis going to the left. And for BC, we have to select coordinates that are described by r and theta, so polar coordinates, and find the values that we have for the deflections. So let's now continue this example. You have it, example 412. You can review it, and we've discussed it before, but just to quickly, that the moment due to AB is, for this section here, is P, we have a P and a Q force. The P has R plus X, and the Q has 2R plus X, and therefore when you take dm by dAB, you get 2R plus X. So this is a preparation stage. Equation 1 and 2, you prepare them because you have to plug them into the integral, and then you do the integration and see that you have quantities that have constant term, x to the power 1, x to the power 2, and then you do integrations. When it's this case, it would be pretty quick and no problem. Then you have the curved section. The curved section, you have to be kind of more thoughtful again here, that you describe your bipolar coordinates. So the moment is q times the total distance. The total distance is r plus r sine theta. And then you have also p times r times sine theta. And when you take the derivative, you get p, we get r times 1 plus sine theta. And then we put them in. Okay, so the point that I wanted to make here is that you will find in such cases that you will have integrals, and the integrals have either sine theta or sine squared theta. So you have to go back and figure out these integrals. So you have to practice on integral of sine theta or cosine theta or sine squared theta or cosine squared theta from 0 to pi over 2. And these are the results. So if you have sine theta, for example, you get 1. If you get sine squared theta, you get pi over 4, and so on. So that part needs to be tightened up in terms of the integrations, so we can get the final results. So that's here at the examples that we've seen so far for failure theory. We're not, in the final exam, we will emphasize material that is past the midterm. So we have failure theory, we talked about it, and we talked about deflection problems because we wanted to know a little bit more about Castigliano's theorem. So now I'm going to go on and continue the discussion to get more examples from the latter part of the class. So the latter part of the class, we have actually described several examples, and these several examples we will discuss here some examples on shaft stresses. So let's start a new share and discuss shaft stresses here. So if we share the screen, then we get a quick discussion on shaft stresses. So when we describe the shafts, we have, due to the action of the forces from the gears, we get bending stress and we get torsion. So we would have an axial stress that is alternating. So if we have an alternating stress, it will have the moment is alternating because the fibers, as I said, the top fibers will be under tension for half of the cycle, and then they come back under compression for the other half. So it is alternating due to the moment. So the moment has an alternating value and a mean value, and the torsion has an alternating value and a mean value. So particularly for round shafts, the polar moment of inertia J is pi d to the power 4 over 32. And the second moment of area I is half of that, so it'll be 64. And then when you put them in, you get these equations 7.3 and 7.4. However, when you look at the action of the moment, the mean value generally is 0 unless it is specified, and the action of the torque, the alternating value of the torque is 0 unless it is specified. So it becomes a little bit simpler, and you can find the von Mises stress, which is sigma alternating square plus 3 tau alternating square to the 1/2, and you can also find the mean stress applied to the shaft. So for shaft design, we start from forces, we find moments, we find torques, we have to also, and then we are able to find stresses. So this is step number 1. Step number 2, we must apply fatigue factors to the material. So we have one column that's the material, one column is the forces leading to stresses. So I have forces, moments, torques, and stress concentration factors. So this is one calculation. On the other side, I have the yield strength, and I can find the fatigue strength of the material, and then I can have modifying factors to determine the actual fatigue strength of the material due to the specific conditions, either surface conditions or diameter or other factors that we have studied. So this is kind of the general idea, and I wanted to kind of discuss one example. So this example to show the procedure is 7.1. You can review it. You get a diameter of 1.1 inch, and going step up to a larger diameter of 1.65 inch. So you have a ratio of lowercase d over capital case D that is used in determining the stress concentration factor at the shoulder. We have a fillet radius that is given to us. So we have R over D also. So between R over D and lowercase d over capital D, we can find the stress concentration factor from the charts. Given bending moments, we given that is alternating. We given torsion that is steady, and therefore the alternating part of the equivalent stress coming from the bending, and the mean, and then the steady part is coming from the torsion. We given properties of material, ultimate strength, and yield strength, and then we are going to go into these two branches. One branch, force leading to stress, one branch, strength leading to determination of fatigue strength of the material. So here is the first branch. We prepare the ratio of the diameters, the R over D, and then we get K sub T. K sub T is a theoretical stress concentration factor in tension. That is figure A15.9. Again, for shear, we have another value, KTS. S for shear is 1.42. So we prepared those, but these are for steady loading. So we have to convert those to corresponding stress concentration factors under fatigue conditions. And that comes in with the notch sensitivity factor. And here it is 0.85 from figure 620, because we know the strength of the material. And the shear value is 0.88. So these are the two figures that can give us the notch sensitivity factors on the tension or axial loading and under shear. Once we get those, then we can convert the stress concentration factors. As you can see here, from 1.68, it comes down to 1.58 on the fatigue. So the stress concentration factor on the fatigue is more forgiving as compared to the steady load. And the same thing for the shear in here. So we did now, we got the stress concentration factors. We have to continue to go from the ultimate and find the SE prime by using correlation, that the fatigue endurance limit is half of the ultimate. And then we start applying the fatigue modification factors, the Ka, Kb, Kcd, and so on. And you can see here, this is the first one, is the surface factor, and the second one is the size factor, and all of the other ones, since we don't have information, then all of the others we set them equal to 1. And that finally gives us the endurance limit that we will use to solve the problem to be 29.3 KSI. Here, the specific case for shaft design, always the alternating moment is given, or you can compute it from forces, and the mean value is 0. On the other hand, the mean value of the torque is fixed, and the alternating value is 0. So they're kind of opposite one another. And that you can, once you have those values, you can find the stresses, and you can apply all of the other failure criteria that we've learned, modified distortion energy Goodman, distortion energy Gerber, ASME, and so on, to find the fatigue safety factor that we're designing for. So I'm going to now stop the share, and we'll discuss one more and final example on gear design from the latter chapters that we have studied in our examples and our lectures. So here I'm going to discuss how you look quickly at gear trains and compound gears, as you see here. So in this example here, we have a compound gear train. We have an input RPM, an output RPM. So we have a gear ratio. If it is greater than 10, we have to break it up into pieces and then start designing. Typically, you can make it as many stages as you want if we have the time. But typically for the exam, it's not going to be more than 2 stages. So we have like a stage 1 and stage 2. We can either have a speed reducer or a speed increaser, and that depends on the input to the output RPM. And we could have a general way of having the relationship between the input axis and the output axis, or we could have some constraint. For example, if we have a compound reverted gear train, then the input axis must be in line with the output axis, and that puts a constraint on the problem that the diameter here, D2 plus D3, should be the same as D4 plus D5. So since the pitch is always chosen to be the same for all 4 gears, and the pitch is the number of teeth divided by the diameter, when you work that out, you find that the constraint is the number of teeth for gear 2 plus 3 should be equal to the number of teeth for gear 4 plus 5. So if we're given a ratio, as an example, we try to break down the ratio so that the ratio of the, let's say if we are increasing the speed or reducing the speed, so at each stage we try to make it as close as possible to the next stage if we want to find exact value. For example, in this case, if we want to have provide an exact 30-to-1 increase in the speed, then we make the 30 to become equal to 5 times 6. So 5 times 6, this is the closest. If we take the square root of 30, it will be fractional. So we don't want to design for fractional speed ratios, and therefore we have n2 over n3 equals 6, n4 over n5 equals 5. And then we have the constraint, n2 plus n3 equals n4 plus n5. So you have 3 equations here to solve for 4 unknowns, because we want n2, n3, n4, and 5. Therefore, we cannot really solve that. So usually there is another constraint, and the last constraint here is that you cannot arbitrarily just kind of find the values of the number of teeth for a gear. There's a minimum number to avoid the interpenetration between the teeth. That's called interference. So if we avoid the interference, we have a formula that we discussed before that determines the minimum number of teeth. In this case, it's 16. So once the minimum number of teeth is known, that fixes one of them, let's say N3 to be 16 or N5 to be 16. And you can solve now 4 equations of 4 unknown. Problem is that if you do that straightforward, some gears are going to have fractional number of teeth, which is not acceptable. So the easiest and best way is to solve, let's say, to find the smallest gear, which is N3 or N5, and fix the number of teeth to unity, and then work out everything in terms of N3. And then you can now multiply, have a common multiplier that is integer to determine all of the numbers of teeth without having fractions. And that's what happened in here. If we set N3 equals 1, we can find N2 to be 6. And then we can now N2 plus N3 would be 7. And then you can solve for all of the teeth, and you find that here's a solution, like you can see here. You find N5 equals 7 over 6. So 7 over 6, it means that if I multiply everything by a factor of 6, or 12, or 18, or 24, then the solution will be valid. So we try to find the minimum number of multiples of 6 that give us N3 to be as close as possible to 16. And in this case, it will be 18, and that can unlock the problem, and we have the final solution. So this is how to choose the number of teeth for a problem like this. The second part that we discuss is force analysis. So you have to be cognizant of force analysis and this relationship between the transmitted horsepower and the RPM. And in particular, we have the pitch line velocity is the pi times d times the RPM over 12. The pitch line velocity is in foot per minute. The 12 is to convert inch per minute to foot per minute. So these are kind of relationships that are important because they give us a connection between the horsepower and the forces. And the forces determine all of the design requirements for the gears and for the shafts themselves. So we should know these relationships, 1335 and 1336, depending on whether we have customer units or SI units. And if we consider that, let me just kind of show some kind of example like this one here, for example, is a bevel gear. So the bevel gears have intersecting axes. So in this case, we have a pinion, and the pinion is running at 600 RPM and is driving the gear. So the gear has bearings at D and C that take the forces. So the pinion is pushing hard at this point here of contact G, and when it's pushing hard, if we know the RPM and the horsepower, we should be able to determine the forces. If we know the forces at point G, there will be three forces basically. One that is tangential, one is axial, one is radial. And we have a triaxial, we have three components of the force, and therefore we have to find, we have to be able to look at vectors in this case to determine all of the reactions and do the design. So here is the pitch line velocity, here is the transmitted load, and then you have the tangential first from the horsepower and the RPM and the pitch line velocity, and then you get the radial and the axial components of the force, and then all of a sudden you have now, this is the contact point G that has three forces, so WR, WA, WT, the contact forces, the reactions, we have to compute them, and these are transverse and these are all transverse reactions at D, and we have decided on C to be where we're going to take the axial force. So the axial force is going to take it at C, but not at D. So applied will be three forces, reactions will be five, two at D and three at C. So there's a little bit of work in terms of balancing on the different planes, the different forces, and finding their values. Here is given by vectors, but you could do it one by one and get the reactions that you need. So these are all examples of what we would kind of be expecting on the final, and we have other features that we in the exams that we have looked before, so you have to be able to review earlier exams as well as the homework assignments. So I wish you all good luck with the final, and if you have any questions, just send me an email, and we will discuss it before the final exam. So we'll see you. Hopefully, we'll see all of you in my next course. I'm offering a course that is a sequel to 96B, and it is on high temperature design. So it's a little bit more advanced, but it will make you a very competent design engineer.